Hello, everyone, and welcome to OA Week 2024. We're going to get started in just a minute to give a few more participants the opportunity to join. All right, I think we can get started. Welcome, everybody, to OA Week 2024 and our session on building capacity. We are delighted to have a big panel for you today, who will be introducing the results of an online survey. And first of all, I would like to welcome you to OA Week, which is sponsored by 4 agencies. First of all is GOA-ON, the Global Ocean Acidification Observing Network. Secondly, the IAEA OAICC, which is the International Atomic Energy Agency Ocean Acidification International Coordination Center. Secondly, then we have NOAA, the United States National Oceanographic and Atmospheric Administration, as well as the Intergovernmental Oceanographic Commission of UNESCO, the United Nations Educational, Scientific and Cultural Organization. So GOA-ON was established in 2012 with a handful of members and has since then grown immensely. We have now over 1,200 members from around 114 countries, as well as 10 regional hubs and 1 sub-regional hub in Africa. And we'll be hearing from most of these hubs throughout OA Week as well. If you're not a member yet, you can join GOA-ON today by visiting GOA-ON.org. OA Week debuted in 2020 and returned in 2021 when events and conferences were postponed due to the global COVID-19 pandemic. And following the successful Ocean and High CO2 World Symposium 2022 in Lima, Peru, we brought back OA Week in 2023 and again this year in 2024 to maintain the momentum around OA research and to provide a virtual platform for the ocean acidification community to exchange their latest findings. As ever, we're thrilled to have such a high interest, to have so many panelists, and to have so many amazing sessions that were proposed by the community this year. During the presentation, all participants are in listen-only mode. You're welcome to type questions into the Q&A box, which you should find at the bottom of your screen. And we'll be monitoring all of those questions and pose them to our panelists after the introductory presentation. You can also use the raise your hand function, and we will then call on you and you can ask your question directly. And with that, I am going to pass it on to our moderators of today. We have Heather Benway from the Woosley Oceanographic Institute in the United States, and Simon Clegg from the School of Environmental Sciences at the University of East Anglia in the UK. So with that, Heather, Simon, please take it away.
Okay. Yes. Okay. Hello, everyone. I'm Simon Clegg. I hope you can see our first slide. I'm sure somebody will tell me if that's not true. So this discussion that we're going to have today arises from a community consultation that we carried out earlier in the year, which established that there is indeed a skills gap and that it's affecting a number of areas of oceanography. And we wrote a report that described the results. You need not have read it today, as I will summarize the main results. And this discussion is intended to inform the purpose, the structure, the content, the types of participants of a workshop to establish what we should do next. We'll be introducing our panel members a little later on. They happen all to be US based, but I should be clear that the problems identified, they're international, which is reflected in the responses to our consultation, and so is the support for what we're doing, and so also will be the workshop. Now, finally, regarding the workshop that we're proposing, and to start off this discussion and focus this discussion today, I'll give you a very short statement from the organization that's likely to be our major funder, and this is it. We're particularly interested in what you envision as the outcomes of the workshop. It seems as though the identification of skills gaps and of impacted subfields have been addressed through the survey and your summary thereof, and so the role of the workshop is to start to chart a path forward. We would like to see your thoughts on how a workshop would approach this crucial step. So that's what we want to help establish today. So we came to this field as a multi-year, since 2015, SCORE and then JCS project focused on chemical speciation in natural waters. And finding collaborators, because there's much too much work for just us, our group, to do, was hard. There's limited experience and ability in the physicochemistry methods that underpin the models that we use. And that's a problem, I think, for us and for others. And worse than this, when sharing the models that are one of the outputs of our projects, is the limited understanding of the chemistry of speciation and how it's all calculated. And this means that a lot of the tools that are out there today have become just black boxes, and that is not a good thing. And so what are the causes of this? Well, the retirement of a generation of leaders in this field, in the underlying chemistry, probably insufficient undergraduate chemistry preparation, graduate level exposure to physical chemistry, and changing preferences among the new young scientists entering the field. I mean, these are just some of the possibilities. So how does this lack of skills affect the broader ocean carbon community? Well, one of the first things that we noticed is interrelationships among the 4 carbonate chemistry variables, kind of limited understanding of the equilibria and equilibrium constants involved, by which, I mean, an example of this I've seen through my work within OXIF, which is the Ocean Carbonate System Intercomparison Forum. Some of the many different data sets giving the equilibrium constants that describe this system, they've been used in some very sophisticated comparisons using oceanographic data, and those are subject of recent papers. But the capability to determine what is the best, most accurate constants independently is is really lacking at the moment. It's quite a poor understanding of the calibration of pH and the interconversion between scales, and this affects measurements and development of self-consistent global data sets. We think the chemistry of MCDR, alterations of seawater chemistry caused by some MCDR intervention and composition change become problematic to deal with without understanding the fundamentals. And integration of treatments of chemical speciation across a range of natural waters, not just seawater. And by this, I mean knowing the values of equilibrium constants for the various reactions just in seawater as a function of salinity is not enough. So these issues, the lack of skills in physical chemistry fundamentals, go beyond our own specialism of acid-base equilibrium. And so we asked the ocean chemistry community what, in general, they think. And in our survey, we asked respondents for details about themselves and made 2 requests for feedback, ideas, proposals, and these were concerning skills gaps in physical chemistry. What are the things that we ought to know that we no longer do? The applications of those particular skills and the needs for capacity building. Then also, what networks or contacts should we engage in this community endeavor to try and help improve things? So we got more than 100 replies and quite extensive written responses to our requests, which was great. And the skills gap and the need to act was really recognized really by everybody. So the survey respondents, they were gratifyingly even across the career stages, away from students and postdocs through to the late career faculty and professionals, very similar numbers. And the geographic location, US and Canada, North America going to dominate, as you might expect. Europe with a very strong showing, and responses from the rest of the world, although fewer, were very helpful and yielded some valuable insights. And I think that pattern, it simply reflects, well, the intensity of research in different areas of the world, and also, to a degree, our ability to get the message out. I mean, I'm familiar with how to do things in the UK, and it's pretty simple there, which is why we did pretty well for our size relative to the rest of Europe, for example. So, and what were the disciplines and the expertise of the responders? So we have the numbers of responders with each expertise in these different areas of chemical activity, of activity, and the top 4 items are in bold red, and we see that looking at all regions, ocean carbonate system, laboratory measurements and instrumentation are strong, followed by trace metals and aqueous geochemistry generally. There are also a number of important subdisciplines: chemical sensors, MCDR, standards and reference materials, paleoceanography. These are all quite strongly represented in the people in these fields by the people who responded. So Heather pulled out just a few of the many comments which are contained in the report. I'll just read 1 or 2 of them. So currently, there's a deficiency in fundamental understanding regarding the dissolution of various minerals, metal speciation across different pH levels, and their effects on diverse biological processes. Then the way aqueous geochemistry is taught, if at all, tends to emphasize applications rather than develop a deep understanding of the fundamentals. And I've interacted with lots of folks who treat carbonate chemistry solvents as black boxes without understanding how they work or which variables might matter in their calculations. So we tried to capture all of the substantive responses in the report. And the next step is to make some sense of community opinion and generate ideas and solutions to these identified problems, which will have broad support. So what we're working towards here today is the next step community workshop. And what we see as the obvious goals, perhaps not the only ones, are to identify key areas and specific skills and expertise that are lacking, and to assess what the impact is on research, commercial activities, monitoring, for example, and then to strategize, to plan how to address these skills gaps in research and in teaching and in capability. And we imagine that such a workshop might have 20, 30 or 40 people. It would contain chemical oceanographers from diverse fields and career stage, with efforts to get representation from different countries, scientists from other fields who have skills we'd like to bring back into oceanography. I think that's an important one. We'd like to involve employers outside of academia, for example, in the MCDR field, and representatives of funding agencies and national chemistry organizations. national chemistry organizations, for example, have some connection to what gets taught, I believe, which would be useful. And finally, representatives of organizations involved in and leading capacity building around the world. So that's a quick summary of the report, and those are our ideas very quickly for what a community workshop might be about. So as the next step, I will ask Heather to introduce us, our panelists.
Thank you, Simon. So I'm really excited to have this group of people here, some of who we've been interacting with throughout this process, and some of whom brought some really great insights to the survey when we sent it out. I'm probably going to go in the order that you appear on the slide here, and I'm going to ask each of you to just speak for 5 minutes about your background and what you bring to this problem and what your perspectives are. I'll start by telling you who I am. My name's Heather Benway. I work here at the Woods Hole Oceanographic Institution and manage the Ocean Carbon and Biogeochemistry Program and Project Office. For those who aren't familiar, OCB is a network of scientists focused on the ocean's role in the global carbon cycle and the response of marine ecosystems and biogeochemistry to environmental change. I am a spokesperson for the program. I work a lot with agency managers and scientists across the field of oceanography and beyond to kind of grow new research areas and identify new funding opportunities. I have worked in areas of paleoceanography, basic chemical oceanography, and so I have kind of a broad research background. I even did fruit fly research when I was an undergrad. So I bring a kind of a broad swath to this role, and it's been a really fun ride. So first, I want to start with Mallory Ringham. Mallory's the lead oceanographer and head of MRV at Ebb Carbon. For those who aren't familiar with MCDR speak, MRV is monitoring, reporting, and verification. Mallory's the lead oceanographer and head of MRV. Ebb is actually a startup that's working to optimize and commercialize electrochemical ocean alkalinity enhancement for marine carbon dioxide removal. Prior to this, Mallory was a postdoc associate at Stony Brook University, and she received her PhD in chemical oceanography right from here, from the MIT Woods Hole Joint Program in 2022. Her graduate research focused on developing and deploying tools for inorganic carbon measurements in a variety of coastal settings. So Mallory, please take it away.
Sure, can you hear me?
Yes.
Audio here? Perfect. So like Heather said, I'm coming from the MCDR industry, and I kind of sit on the border of the startup space with a number of different academic and federal research projects that I've been working on. Ebb is one of the startups that is unsurprisingly based in Silicon Valley, and we are working on pilots in the Pacific Northwest and Washington states. There's a lot of really interesting and exciting research happening in this field. And I think that's where I want to focus my comments, is that MCDR has the promise to make a lot of money and to be a pathway for a lot of folks who are coming out of acidification PhDs, out of general ocean chemistry, physical oceanography. So we're seeing folks being snapped up by this industry that is new and is trying to find its footing in how we do anything related to measurement and verification across sensing, sampling, modeling. And that means that there's a lot of scrutiny on this space, and there are intense demands for data that are coming out of pilot laboratory experiments, pilot facilities, field experiments. And that's a challenge in itself. High quality and real-time measurements for carbon chemistry variables is hard to do. So we're lacking in capacity, both in hardware and personnel, and we're feeling that on the startup side in a couple of different ways. One is in a lack of personnel who understand the type of measurement that we need to have to assess whether MCDR works, and that's in a range of different fields. We work with compliance from permitting groups that have an understanding of how to do pH in wastewater or freshwater, but tying that back to saltwater. means we're often not talking on the same scales, the same types of measurements, the same sensors, which is a challenge. We see differences in alkalinity titrations depending on what range of pH we would actually like to operate in. And like Simon mentioned, MCDR inherently changes the seawater properties that we would like to focus on. So if we're shifting salinity and various carbonate parameters because we want to work with brines from desalination, or if we want to work in river outfalls, there's a lot of different pitfalls if we're seeing carbonate chemistry as kind of a black box, things that we feed into CO2 sys. On top of that, we're figuring out the standards, the protocols, how we develop the data management strategies in real time. And often that work is being done by a range of different actors. There's MCDR companies that are writing protocols, there's nonprofits, there's carbon registries, and each of those groups don't always have seawater carbonate chemists on hand. And so we've sometimes seen impractical requirements or recommendations for the types of measurements that we would like to have, like real-time high-resolution alkalinity in situ, but that we don't have a practical way to buy things and put them in the water, especially if you're coming from an industry that's trying to spend its capital funds in different ways. So I'm coming to this workshop idea as someone who has hired folks who are interested in getting into the MCDR space. And unfortunately, that means if we're trying to hire people who are qualified to do this work, we may be pulling them out of NOAA Carbon Group or out of other organizations that really need to retain personnel and capacity. We're also seeing a lot of push for bringing in early career scientists. And from that, there's a range of different ways that programs are educating students. When I went through Woods Hole, we had the full range of carbonate chemistry data that you would run by hand. Other programs are just, here's CO2 sys and an Excel macro. Other programs are more robust and are using various types of useful modeling tracks. So I know that MCDR isn't the main focus of this workshop, but it is a place that we can see already a bit of a bleed off of personnel from other academic spaces that need this carbonate chemistry capacity. And that's without touching on anything else that we'd like to think about, how the nitrate cycle reacts when we're thinking about carbonate changes and how do we model that and so on. So yeah, I would love to see workshops in which we bring a source of truth to this field about what can be measured, how it can be measured, best practices, how do we train folks to do this. Happy to talk about any of those topics.
Thank you, Mallory. That's fantastic. So let's go on to Ryan Woosley. Ryan is a principal research scientist at the Center for Sustainability Science and Strategy at Massachusetts Institute of Technology. He is a marine physical chemist focused on the carbon cycle and ocean acidification. And to date, he's focused on quantifying the uptake and storage of anthropogenic carbon in the ocean over decadal timescales utilizing repeat hydrography cruises. Go ahead, Ryan.
Thank you, Heather. So as Heather said, I'm very interested in anthropogenic carbon and how the oceans are responding to this CO2 that we're releasing into the atmosphere. We've been very lucky that the oceans have been able to take up a significant portion of the anthropogenic emissions, but of course that has impacts on the ocean itself and the resources we use it for. So I've focused a lot on observations and making direct measurements, the high quality, the best alkalinity, pH, DIC, PCO2 measurements that we can. I've also done some work on physical chemistry itself. My PhD was on physical chemistry of minor components of seawater. So I have experience with the equation of state and Pitzer modeling and dissociation constants as well, although I focus more on ocean acidification now. Yeah, I agree with a lot of what Mallory has said and how MCDR is a growing space, and in order for it to work and be successful, we need to understand the basic chemistry that goes on. For various reasons, we seem to have lost some of that. Part of it is, those big names in the field have retired or approaching retirement, and new replacements haven't come in. But there's also been some lack of just general knowledge and just basic knowledge in general that's not passed on through classes or experience to people who don't work in the hardcore physical chemistry of seawater. And so I'm very excited about how we can think about these things and kind of improve that gap that we've identified here. You know, with AI and machine learning, there's been kind of this shift just in general in oceanography towards big data. And we want to make sure that while we use these new tools and they're very important, that we don't lose that knowledge that allowed them to be, that go into the data behind those things. So I think it's very important that we maintain our roots as we go through new era of AI and machine learning. So yeah, I think that's just kind of my perspective.
Thank you, Ryan. What a great note to end on. Not losing touch with our core knowledge about the origin of the data themselves. I want to introduce now Katelyn Schockman, who is a University of Miami Cooperative Institute postdoctoral scientist at NOAA's Atlantic Oceanographic and Meteorological Laboratory. Katelyn works with the Ocean Carbon Cycle Group by applying her expertise in marine physical chemistry of the inorganic carbon system in seawater to start a pilot project to produce seawater reference materials, as well as better characterizing the composition of seawater to improve projections of future changes in the ocean due to ocean acidification and climate change. Take it away, Katelyn.
Perfect. Thank you, Heather, for that introduction. So like Heather mentioned, I'm a postdoc and working at University of Miami at NOAA's lab. So during my PhD, I focused mainly on the carbonate dissociation constants, specifically in seawater. My work used mainly lab-based techniques to characterize the dissociation constants for a range of temperature and salinity. And so this work really delved into the weeds about the physical chemical characteristics of seawater. And now as a postdoc, I'm working to develop the inorganic carbon reference materials at NOAA to help fill this community need for RMs, for high quality inorganic carbon measurements. And also I'm a member of the OXIF community, which Simon mentioned, working to learn about the uncertainties and actually quantifying those types of things for the carbon parameters. So from my perspective, coming as an early career researcher, I kind of have like 3 points I'd like to highlight. First, I sense that early career students are being less exposed to, the detailed intricacies of physical chemistry. Many of my peers either were never exposed or very minimally exposed to like this type of coursework. And, I think see this as a lack of faculty to actually teach this type of work. And also less students coming in with like a hard chemistry background that are interested in the marine science space. So, it can also be difficult to seek out this type of coursework if there aren't faculty at your specific institution that have the expertise that you're after. And then, as has been mentioned, as experts in our field begin to retire, these types of courses can become even more difficult to find. Secondly, coming from someone who does experimental work, I kind of sense there's a disconnect between those of us studying aspects of physical chemistry from an experimental point of view versus those of us who are using modeling points of view. And I think both are equally important. And so there could be some more working together amongst those different camps. And then, related to this, I think there's also limitations to both avenues that maybe aren't fully appreciated right now. And then third, I think it and this has also kind of been said too, I think it's becoming easier for researchers to get around having a fundamental knowledge of the physical chemistry of seawater. So, it's quite feasible these days for someone to download carbon data and plug it into CO2 sys and calculate whatever they want without really knowing what they're calculating. You can choose an arbitrary set of dissociation constants without knowing what the implications for that are. And then related to this, when a program spits out the calculated values, it can be easy just to accept those results at face value without actually thinking like, are these results feasible or not? Maybe there are acid-base reactions that we haven't considered, or there's aspects of organic material that haven't been included, or the temperature and pressure dependencies aren't fully constrained. So just to give a few examples of where I see things going wrong. And then also related to this, it's quite easy these days to buy off-the-shelf instruments to measure the carbon parameters without actually knowing how to use them correctly, or the standards and best practices. And so that can also become problematic. And this third area, I think, is where a proposed workshop could kind of address some of these issues with hands-on learning and information about details about calculations, or like how to actually use these measurements. So overall, I think it's important that we're highlighting these gaps. And I also think it's especially important to include the early career group into consideration, as the giants of seawater physical chemistry are starting to retire, and we need new minds to kind of fill these gaps. So thank you very much.
So many good points there. I'm not sure I know where to start. I'm really excited for our discussion. Thank you so much, Katelyn. Now I want to introduce Erica Ombres, who is program manager with the NOAA Ocean Acidification program. As a program manager there, she oversees a talented team that manages OAP's nearly 100 internal and external grants and projects. She builds coalitions and collaborators, including NOAA and other federal program managers, to create more effective research opportunities. In this role, she also provides strategic guidance for future funding opportunity directions and works to create an interdisciplinary community of OA research practitioners. And I work with her on lots of things, and I can attest that she is a superstar. So Erica, welcome.
Heather, thank you for such a great introduction. And it's so great to see so many familiar faces on this call. I want to just echo what Ryan, Mallory, and Katelyn have already said. Especially that we really need to understand the mechanistics before we can fully utilize all these new data science tools and models that everyone is so excited about rolling out, especially, as Mallory mentioned, with all the new interest in marine carbon dioxide removal. From my vantage point as a program manager, I see a lot of proposals. And I work really hard to get great reviewers to critically review those proposals. And I can say it is really challenging in this field that is so interdisciplinary to get reviewers that have the basic mechanistic understanding that Katelyn was mentioning, and that also understand the biology, or, even further, we're moving more in our program into also understanding social science. And so getting different reviewers who have these different expertise is very challenging. And I can attest to the fact that the mechanistic carbonate chemistry, it's hard to get those reviewers, the leaders and giants in the field. They are retiring, and they're highly collaborative because there are not that many of them, which makes the finding of reviewers even more challenging, but so crucial to point out these instances, like Katelyn mentioned, where people are using things inappropriately or may not fully understand the mechanistics, and pointing that out in the review period when you can make tweaks or add partners on to improve the science that's being produced. And also, over my 10 years as a program manager, seeing a shift in the science, and also, as Katelyn mentioned, as early careers who are coming into the field, and a shift away from those who are looking at basic mechanistic understanding to those who really want to do more applied work. And coming with that switch in perspective and focus on more applied work, you bring in this need for an interdisciplinary nature. And as Katelyn mentioned, there tends to be less and less of those who have that mechanistic base as an underpinning understanding and a foundation for the rest of their research portfolio. So I'm really excited to work with the rest of this group and come up with some potential recommendations for a workshop, and excited to see how this group moves forward. And I also wanted to second, Katelyn, your comment about sometimes the disconnect between experimentalists or those in the field collecting observations and modelers, and that's that black box disconnect between sort of that understanding of the mechanism and then applying it as an equation that will maybe fix whatever weirdness you're seeing in your model. And so really want to highlight that and hope that we can come up with some great recommendations for this group moving forward. Thanks.
Thank you, Erica. Now I would like to introduce Emily Bockmon, who is oh, wait, no, I'm sorry. I'm going out of order. I have to stay in order here. I want to introduce Clifton Buck, actually. Clifton is an associate professor and graduate coordinator at Skidaway Institute, University of Georgia. He is a chemical oceanographer with broad interests in the cycling of trace elements in the ocean. Trace elements are present in small quantities, but exert tremendous influence on the capacity of the surface ocean to support life. For example, much of the primary production in the ocean is limited by the availability of the micronutrient iron, which I'm sure you're all familiar with. Much of the work done by Clifton's research group is focused on understanding how iron enters the marine environment. And for those of you who, one of the things that really prompted us to realize this gap in capacity was working on a speciation model, a marine speciation model. And half of that work has focused on trace metals. So I'm really excited to have Clifton's expertise on this panel and her perspectives. So go ahead, Clifton.
Well, thank you, Heather. That was great, and saved me some of the things I was going to say. So I appreciate that. Yes, I'm very excited to be here because this has been something that we've identified within kind of the trace metal community as well. This kind of growing gap in knowledge of physical chemistry and what our students are able to do. So I'm an observational chemical oceanographer, so I spend a lot of time in the field and kind of cut my teeth on CLIVAR, which became GOSHIP, and then geotraces. So I have a lot of experience kind of in that, interacting with the carbon community as well. I think I'm probably primarily here in my role, essentially as kind of an instructor and faculty member, given my research interests being a little bit outside the focus. So just as kind of context, I'm based at a U.S. research university that confers master's and PhD degrees. And what I've seen is that largely much of our student body is focused on the kind of the biological and ecological kind of microbial ecology. We're getting in more and more into bioinformatics, like Ryan was kind of referencing in terms of big data and omics and all of these things. These have been the hot topics, and I think what we've started to lose is that connection with some of what I would call the basics. I'm kind of reminded of that old saying where we're standing on the shoulders of giants, right, in the field. The problem is, I think we're starting to forget what they did, and now we're losing that foundation. I've got some theories on why some of that might be, but certainly in my 11 years as a faculty member, and especially in my position now as the graduate program coordinator for our department, so I get a chance to see kind of all the applications that come in to our department. So some of this is a bit anecdotal, and I apologize for that, but I definitely see a move away from kind of the hard basic science in the undergraduate level. And so, we're getting more and more applications with students having an undergraduate degree in environmental science or some more larger scale system science. And I think what that means is, and it's not to say that they can't be successful, but they've had less of that preparation if we're going to be very chemistry biased about it, maybe they've only taken a handful of semesters of chemistry, and maybe they didn't have to take P-Chem in order to satisfy their degree. So they're coming to us kind of without some of that fundamental basic understanding or that experience. And I think that kind of reinforces itself at the graduate level, where these things become kind of, they have this aura of scariness, right? And so it gets harder and harder to attract students to these types of courses that will be challenging. But I think that are fundamentally, most people would agree, are vitally important. So this leads to a challenge of, even if a faculty member develops courses to address some of these knowledge gaps we're talking about, are they, maybe their individual institution, are they going to get enough enrollment to make sure their classes make, and so these are challenges that individual faculty or groups of chemical oceanographers are dealing with at their home institutions. And then, so what I'm ultimately concerned is that these fundamental concepts of thermodynamics and kinetics in the ocean are being relegated to maybe a week in that core chemical oceanography course, or a handful of pages in a textbook, and that, whereas, at least in my own experience, I took a whole course on aquatic chemistry from the Stumann-Morgan textbook, and I'm worried that some of that is not being transferred to today's students. So ultimately, my hopes are that the outcomes of a workshop like being discussed here are, something along the lines of a white paper that includes specific physical chemistry centric student learning outcomes. What is it that the field thinks every chemical oceanographer needs to know? Because that can help set that baseline across the community, so we know we're preparing our students for the challenges ahead of them. And in addition to that, something like accompanying modules of instruction, again, so that, there's lots of experts on this call that would be involved. What are the best practices? What are the best ways to teach this material in a really effective way that can help better prepare our students? So I'm excited to have that conversation. Thanks.
That's incredibly helpful from a curricular standpoint. So thank you so much for that, Clifton. I love the idea of student learning outcomes, kind of standardizing this for our community to address this problem. Now I will introduce Emily Bockmon, who is an associate professor in chemical oceanography at the California Polytechnic State University. Dr. Bockmon is an expert in seawater carbon dioxide measurements. Her current projects include characterization of the Central California coastal environment, including Morro Bay Estuary, using both discrete data and autonomous measurements. Emily is also currently the Associate Director of the Center for Coastal Marine Sciences at Cal Poly. Take it away, Emily.
Thank you, Heather. This feels like a perfect place for me to start following up on what Cliff has said. Since my PhD, I've really devoted my career to teaching chemistry and educating future chemical oceanographers and other interested undergraduate students. And so as I think about, sort of the problems that everyone before has brought up, right? Like I agree with much of what has been said. I am really thinking about this problem from the perspective of an educator and the perspective of an educator sort of at the beginning of the trajectory. And hopeful that we can think of like what a pipeline might look like to sort of fix this problem, not just in the short term in terms of what's missing right now, right? Like things that we wish we knew right now that we don't, or expertise positions that we wish existed, but also like what things will look like in 5, 10, 15, 20 years, because I see a longer trajectory problem. And I think this is well outlined, but I see that longer trajectory problem as well as sort of the current gaps. And so, I teach undergraduate marine chemistry and I contribute to a marine science major, and I have a lot of misgivings that Cliff identified in terms of them being very well educated in interdisciplinary marine science, but not well educated in any particular, hard science or specific science that gives them a really intense background that does prepare them for in-depth studies, whether it's in, physical marine chemistry or some biological study. But I also run my research is fully done by undergraduate students. I advise, between 9 and 12 undergraduates at a time. And so I see so much potential, I guess. And I interact with a lot of chemistry majors who actually would love to be involved in this field and I think are well qualified, they have taken all 3/4 of physical chemistry, right? They're excited to get into the weeds of difficult chemistry questions. And so I guess I'm hoping to bring a perspective of optimism to this group in this workshop, in that I think that if we can provide opportunities of where to send those students, there is a possibility, to grow this and sort of solve this problem. My students struggle kind of on the flip side of what was sort of said, is that they actually would like to study the chemistry. They would actually like to focus on the chemistry, and they don't have the modeling skills, right? They don't want to become biogeochemical modelers, or they want to focus on the chemistry. They don't want to also kind of do the ecology of, an intertidal or nearshore environment. And so, but I don't exactly know where to send them right now to continue their education. And so that's where I feel like there's actually a gap, is in our graduate level education in really hard chemistry. A lot of, I guess maybe I don't count as early career anymore, but my early career, mid-career colleagues here, a lot are working for NOAA or working for NIST, or aren't in traditional academic environments where they are accepting and educating graduate students. And so I see that there's also a little bit of a gap right there. How do we get students from undergrad into these graduate programs so that we can train them in sort of deeper physical chemistry, training? Yeah, so I guess that's kind of the perspective that I'm hoping to bring, and hoping to be a part of the solution sort of through this workshop, because I do think I do see the problem from this perspective, but I'm hopeful that we can solve it.
Thank you so much, Emily. That's a great perspective in terms of thinking a little further down the pipeline and what we need to address, especially if some of the giants of hardcore physical chemistry are retiring, and the labs that do these kinds of measurements they're not nearly as many as there used to be.
Yeah, I need Ryan and Katelyn and Mallory to get academic positions, and I'll send them graduate students.
All right. Our last panelist of today is Jess Adkins, who is a Smits Family Professor of Geochemistry and Global Environmental Science at Caltech. And Jess is also the co-founder and CEO of Calcarea. Jess is an oceanographer, climate scientist, and geochemist by training. As a professor at Caltech, he has mentored students and conducted research on coral biomineralization, paleoclimate, the coupled sulfur and carbon cycles, and the dissolution rate of calcium carbonate in the ocean. It is this later work that led to the founding of Calcarea, so that we can take the Earth's natural CO2 buffering mechanism and apply it to decarbonization of shipping. So, Jess, take it away.
Thank you, Heather. And thank you, everyone. I think I will uncharacteristically try to be brief, because you've been listening to a lot of introductions, and it'll be fun to get to hear the panelists. I'm looking forward to learning a lot. I guess I would say I'm part of the problem. Like I definitely can't call myself an early career scientist anymore. And I've been teaching for 25 years of classes that have the titles that should have been covering this kind of material. And yet there's this gap. And so I think that the problem could land at mine and my colleagues' feet. So I apologize for that. I guess I see three possible ways we might divide this up, and then I'll have like a little bit of a soapbox or idea at the end. But there's just a theoretical side, right, that comes on physical chemistry. And this is kind of like, what are you going to go decide to put into a curriculum of a class? And I was a chemistry undergraduate, and every time that I was confronted with the thermodynamics of a system and activity coefficients, the assumption was, well, let's just start from infinite dilution and see if we can go from there. And so I don't know how much we should expect of our incoming students, right? They're being told to avoid the most interesting parts of the complicated soup that is seawater in terms of all the non-ideality. And so we could talk about that theoretical part. Then we've touched a couple of times on ability to make sort of basic measurements. I think folks are thinking about like grand titrations here, or how to measure DIC, or even how to measure pH in seawater. And we could have an interesting conversation just about that piece about, does everybody need to know how to run a grand titration? Maybe not, right? But that would be an interesting part to talk about. And then there's a third one of like, what are the pieces that we actually don't know? Like, there you can take the triplet of alkalinity, DIC, and pH as they exist in reputable databases, and outside of the surface ocean, the values that you would calculate for carbonate ion don't agree if you try the different doubles. Why is that? Like, there's open research questions still there. So those are kind of three categories that I think about it in. And then I got going down with my friend Will Burleson this pathway of doing lab experiments on dissolution rates in the ocean. We had a couple of motivations for why we wanted to do that. One of mine was quite personal, and that's because I love going to the field. I absolutely adore that aspect of oceanography, but I had young kids. And my daughter was wondering where I was when she would get driven home from daycare. I'm going to start crying here in this memory, and because I'd been away for 6 weeks at sea in the Southern Ocean, and so I really was motivated to find something I could do just in the lab and not have to be out traveling all the time. And there's a real bias in our field against lab experiments, that the ocean is so complicated. I got told this many times in graduate school, and sort of internalized it in a deep way, that the only way we can really learn about things is actually making measurements out in the ocean. And I've learned a ton from going after the kinetics of the dissolution rates of calcium carbonates in the ocean, just as lab experiments that then led to, of course, more field work. My kids had gotten older at that point. They didn't care that I was around or not. That has been just fun. I don't, you have to find, I guess, people who find that kind of work really interesting. I did get asked by a very good friend of mine at MIT, a physical oceanographer, who I respect a lot, when I was walking him through, like, look how cool it is. There's like these mode changes in the way the dissolution goes. Like, you move from step edge to etch pit and like all this craziness. And he looked at me like, why are you working on this, Jess? Like, what how does it matter? And my first thought was, well, it's just fun. That's like the best part about the job, is that you get to pursue your curiosity. But it was sort of right, like, to put that question to us. Like, I don't know that we should necessarily sit here wagging our finger too much about, like, you don't understand enough about the Coulombic versus ion pairing contributions to activity coefficients and this. But I think I've come up at least with my own version of an answer for that, and I'll finish there and shut up. But I try to write down the descriptions of how a system works as a set of differential equations on kind of any problem that I'm working on. And I think the beautiful part about being an environmental scientist or being a chemical oceanographer, as opposed to being just a chemist, right, is that it's the gradients in the environment that are telling us the information about what's going on, which means you automatically need to know about transport in order to understand how the chemistry is telling you, those gradients are telling you about the chemistry, which means when you write down that set of differential equations, you're trying to incorporate a bunch of information from different slices. And if you could understand what, say, the kinetics of your system were, then they become explicit terms that you know inside those sets of differential equations, and they release the gradients to be able to tell you about something else that you might really want to learn about, or they are the thing that explains the gradients, and you solve the problem, and you can go on. And to me, that's the why, that's the motivation. And it's been hugely important at Calcarea that we understand the dissolution rate of calcium carbonate in the ocean, because all the other things that come into the chemical engineering of what we're trying to do, we can go after those knobs without having to worry about, oh, wait, is this all because, am I not getting enough alkalinity out of my system because I just don't understand the first order rate constant, or why there's an exponent of n in this funny rate law that looks like an empirical curve fit. If you actually understand the basics of what's there, it lets other pieces of the system shine through. And I think that's been, for me, like the most fun part about working on this kind of nitty-gritty of kinetics or physical chemistry. And so I hope in the end it's fun, I guess, is my final thought.
Thanks, Jess. That adds a really nice, it adds a nice piece, or a nice perspective to the discussion. And I always knew that Diffie-Q was going to come back to haunt me. I just didn't know I would be in my 50s when it happened. But thank you for that perspective. I think that there's going to be a fantastic discussion. I'm going to ask Simon to share the next slide, and I'm going to drop a link into the chat. Simon, why don't you, there's a QR code for those of you who happen to be on your phones. And for those of you who are on your computers, you can join us in this Google Doc. You can either do the tiny URL there, or there's a longer link in the chat here to get you into the doc. If you don't use Google Doc, feel free to dump stuff into the Q&A, email us, whatever you'd like to do. And I know that we have a question in the chat, or in the Q&A here as well. And I would actually like to address that before we get into the workshop nitty-gritty that we have planned here. So Maribel put in the Q&A, I think that part of the shift from basic to applied science is based on the fact that that's where the funding goes, which has certainly been the case with MCDR over the last couple of years. How do you think this can be overcome? Would any of our panelists like to address that?
I don't have, oh, Erica, she raised her hand.
Well, I mean, you can go as well, Emily, but I was going to say, as a funder, I probably have to answer this, right? I agree 100%, Maribel, that people and students will go where the funding goes. But I think it's beyond just that, because NSF, this is what they do. They do basic mechanistic research. So I think it's beyond just early careers, or like this next generation of scientists going where the funding goes. I think it's also this next generation of scientists wanting to have more applied research, wanting to help fix all of the problems they're seeing in the environment. I know myself, when I was in graduate school, my advisor kept telling me, you don't have to go there. Like, we're funded by NSF. Like, just just do your research. You don't have to worry about these problems. But I wanted to. Like, I wanted to think about that and make those connections. And I see that in a lot of the next generation of scientists as well. It's not to say that we also need the mechanistics, right? Like Clifton was saying, we need someone to stand, we need to stand on that foundational knowledge. So we need both. I don't know if we have anyone from NSF here today who might want to drop in the chat their thoughts, or Emily, if you wanted to jump in with your additional thoughts on that. But from my perspective, that's what I see.
Oh, I was just going to say that, Heather mentioned MCDR as an example of where current funding is, and therefore where focus is, which I think we here would all argue that the base level mechanistic physical chemistry should be a part of that outcome. But even I think it goes 10, 15 20 years back to ocean acidification, right? Becoming, the reason we're all here this week in this webinar, but a huge emphasis was placed on ocean acidification and the measurements exploded, right? But not necessarily still that emphasis on basic research. And so I think I don't have an answer to Maribel besides I think it's a very good point, right? That I do think that the research goes a little bit where the funding goes, right? I think that is true. And I think there's, less luxury to study. Listening to Jess say, that he's just pursuing these things that are really interesting to him it feels a little bit like a luxury in today's funding environment. You have to be very clever to figure out how to fund things like that. And so, yeah, I don't have a solution, but I do think that's part of it.
Yeah, and I mean, even like the leaders in the field, I mean, even Andrew Dixon has struggled to get that like work funded by NSF, who funds this type of work. So it's, yeah, 100% agree with you, Emily. And I don't know, give us more money. Maybe we can see what we do.
If Andrew can't get it funded, how am I going to get it funded,
Oh, Heather, you're still muted.
Sorry. What we've done here is we've organized the Google Doc to kind of take us through the discussion and invite you to raise your hand and speak up, or type stuff into the Q&A, or type stuff into the Google Doc on these various topics. And the first one we want to hear from you on is your perspective. Do you think we're crazy? Do you have different perspectives or facets of chemistry that you think are big and concerning gaps? And so we'll just kind of go in order. Feel free to skip around in the doc if you're very motivated. But we wanted to start with your perspectives on gaps. And what we've done here on these slides is we put down our thoughts, which we really already conveyed to you, but we want to hear from you on what your thoughts are. What are your perspectives or perceptions of skills gaps in this area?
Yeah, I'll just add, Heather, that we have 7 guide questions, but they are only guides. So please, panel, please, others, do raise other questions. So as Heather says, this first slide question is, what are people's perceptions of the skill gaps? What do you think they are? And what we've written out there as our thoughts are really things that have already come up. So what do you think, panel, others, about those? But more particularly, what are we missing? What else is there?
Jess, go ahead.
I guess there's like, I have 18 things to say and yet nothing to say, and so that's dangerous. One thing I would say about just returning to one of the things I mentioned in my introduction was just, I think we should directly address this bias to go out and observe the ocean as opposed to go out and try and simulate it. It's not, I don't mean in silico, I mean in chemical experiments in the lab. I want to leave in silico aside for a bit. Because I really think it's a pretty strong bias that I internalized when I was in graduate school, long time ago. And I think more examples of demonstrating where lab experiments have led to greater insight about the big data sets or about somebody's field program would be really helpful and inspirational to me and to folks in general that were interested in not rolling around on the ship necessarily, but using basic measurements or well-posed measurements and experiments in the lab with the goal, of course, to try to understand why are the gradients out there that we see in space and time. I think that could be an important part of the workshop, is just sort of directly addressing, including getting folks who think, come on, why are you going and doing all those lab experiments? It's totally undersampled out there. We still don't even know what the actual gradients are, right? Let's not waste time in going, I'm making up a straw man here. But I think that would be a good part to put into a workshop.
I'll jump on that one and follow that up with a comment that in our branch of NCDR where we're doing alkalinity enhancement, we don't expect to be able to measure anything that is actually a signal of what we are doing outside of a specific small mixing zone. So our only method of actually capturing and characterizing some of the carbonate system that we're messing with is in lab experiments. And so we've been doing that, applying different sensors, different types of measurements in this lab context. And even there, we see that there's quite a lot of a difference between your DIC and alkalinity bottle samples versus various sensors. So there is the capacity on how do you even know what types of sensors and equipment to choose for these lab experiments. But we've also seen some hesitation in interest in those types of lab experiments, which is challenging. And an example of that is I spent my postdoc at Stony Brook working on 6,000 liter tank experiments for alkalinity enhancement. So we're moving from the benchtop beaker to a larger tank and then to field experiments. And almost every reviewer on the paper that we first generated from that project said, what's the point of this? You know, why aren't you doing this in the ocean? So it's a bit challenging when you look at, you know, who's reviewing from biogeosciences and some of these other journals around first the perceived need for these types of experiments that mimic in the field, which some groups are seeing as very critical. If you're thinking about biological impacts, you want to see these lab experiments first and have every bit of intermediate information. But if you're thinking more on like the large scale impacts of this type of technology, just skip it and do the field trial already, right? So there's some challenging dynamics in how we even describe the types of lab experiments that may be our only direct way to inform the types of field trials, which are inevitably going to be challenging to apply if you haven't tested them in a lab first. So just throwing some weight behind Jess. And sometimes it's difficult to justify that in a proposal, right? And so if you're putting this into NSF, it's way too applied. If you're putting this into DOE, it's not applied enough. And if you're trying to find a technician to do the actual measurements for any of this, you're out of luck. So.
Okay, thanks, Mallory. Is there anybody else who'd like to say anything? Are you seeing anything in the chat, Heather?
Nope. We're going along. We should move along, actually. It's 12:08 already. This went by too fast.
It has,
Can
it has, or it is.
quickly jump in before we move on, Heather and Simon?
Mm.
I just want to add on to what Jess and Mallory have said. You know, yes, the mechanistics and the experiments, and we need those people to talk to the observers and the modelers so that they can appropriately incorporate it in, because like Mallory said, we can't observe everything everywhere. And we need those models to really understand the mechanistics in order to get to the next level. So not everyone needs to know everything, but maybe some of that basic training that Clifton was talking about in their graduate school chemistry classes so that they understand that, you know, not everything can just be put into a black box solver.
Okay, thanks, Erica. Right, so we will move forward. So, how to address those skills gaps? The need for multiple angles to this, we think. Teaching and preparation, we've heard a bit about that. Research and analytical capacity in graduate programs, summer schools, research exchanges, and then community building activities that bring together relevant fields, you know, not just within our own, to facilitate regular scientific exchanges and improve collaboration across fields. And metrology plus oceanography is a very interesting one. Interacting with metrologists is an education, and they would say the same about us. So let's discuss some of that. Who on the panel would like to begin?
So
Brian.
I'll start. So I think there's, you know, two different angles to look at this. So one way to address the gaps is to bring in new experts. So bringing in a physical chemist that's not an oceanographer and training up new experts to replace those that are retiring. And then you also have the teaching and education. What does the average chemical oceanographer need to know? So what's the baseline knowledge that every oceanographer should know versus what the experts need to know? Everybody maybe needs to know how to calibrate a pH measurement to study this, but do you need to understand why we have the different pH scales, or just to know that they're there and which one is appropriate? And so I think one outcome of the workshop could be defining this is what everyone needs to know, and these are the types of experts that we need to recruit into the field.
Yeah.
Cliff, go ahead.
Yeah, I don't want to, belabor or anything, but I totally agree with Ryan. And we're actively, in my department, we're having this conversation about, what is it that all marine scientists need to know versus what is it that chemical oceanographers need to know. And I would just add that, again, just in the interactions that I have, there's often a tension between, faculty members have different perceptions about value added from like coursework versus what students learn in the lab. And again, I think, what's important, I think, to come from all of this is something that truly we can hang our hat on, that, your students will benefit from learning these concepts, and it's a valuable investment of their time. And in that way, we start to see a broader understanding. There's an additional comment that was already answered in the Q&A about, the mathematical preparation, the math skills that students have. And that's absolutely, we see it too. And of course, we're directed by our higher ups that we're supposed to meet the students where they are, which I agree. We have to deal with, we handle who comes to our program. And so, but I guess it's just indicative of lots of different factors that are contributing to what we are observing as a skills gap kind of at the end of the road. So that I think really, again, in a larger workshop, we can, the participants can start to look at this question from these various angles and have a more cohesive guiding document or principle that comes out of it, that then, that the community can then kind of, again, hang their hat on as we recognize all these challenges. These are potential solutions, and the whole community will benefit.
Yeah, I think there's a fundamental fear of math and science. It starts at a young age, and it needs to be addressed at every level of education. Of course, we're focusing mostly here on undergrad and graduate, but couldn't agree more. And math is one of those fundamentals. Jess was talking about DiffyQ. I mean, we apply these things in all of the chemistry that we do. Does anybody else have any relevant comments on this topic? And remember, you can also be typing into the Google Doc. This is going to stay open. We're not doing anything with the Google Doc. It'll just stay open. So you can add feedback whenever you have the time. Or if you think of something at 3 a.m., feel free to wake up and start typing. Okay. Do you want to move to the next topic, Simon?
Sure.
I don't see hands up, and I don't see any new
Oops.
questions.
Pardon me. Oops. Okay, so intended impacts of whatever we may do, what of actions to address the skills gaps. So our thoughts were that one would expect to see improved chemistry preparation and exposure to lab techniques, models at both undergraduate and graduate levels, improved capabilities in key physical chemistry dominated applications, MCDR being one, in natural water chemistry, better recruitment and retention, that would always be good, and perhaps figuring out new mechanisms for capacity building or capacity maintenance and sharing, that would mean that if we're able to get out of this skills gap, how we might stay out. in future, which in one word probably means vigilance, but we can see what people say about that. So back to the panel on impacts.
I'll take a quick stab at something that I would like to see, and I just dropped this in the document. I'm finding a lot of times that we have students or folks who are coming into this space from other branches of different types of oceanography, moving into MCDR world, who don't really have a great idea of where to find resources for carbonate chemistry in particular, and aren't familiar with GOA-ON or SOLAS or some of these other networks and forums that already exist that are underutilized. So if that is something that could be incorporated into coursework of any kind so that we are actually teaching students where to find this information, that would be great. And I'm also finding a lot of early career folks who are coming out of even PhDs who don't have a good idea of where to find existing data from BGO-DEMO, from NOAA NCEI. It's not really taught in a lot of courses where to actually pull this information out, and therefore you wouldn't have a great idea how to look at the metadata and decide, is this good pH data or bad, and that's a big gap in just finding information for both experiments and lab setups and modeling world.
And I've been thinking about this. This is a different perspective. Since Emily brought this up, I was really glad to hear, Emily, that you have students who are like so excited to dive into the nitty-gritty of the chemistry. Because I've been wondering, what fields are they going into if they're not going into ocean science? And how are we missing them in the pipeline? And how can we recapture them? Is this talking to other divisions at our universities? Is this making cross division or cross topic area seminars, talking about how cool ocean science is in these spaces? I just talked to a bunch of third graders this week, tough crowd, but I was really plugging the engineering and the coolness of ocean science. So fingers crossed, we'll see what we get from that. But I'm curious, from those of you who are teaching, where do you think we're losing these people who are super into the nitty gritty of the chemistry?
Katelyn, go ahead. Why don't you have your hand up? Happy to have you go before.
Okay. I just want to say, from a perspective of an early career, so I got my undergrad in chemistry, and I kind of found marine chemistry almost by, I didn't actually know about the field. It was kind of by chance. And I feel like there's a lot of good chemistry students, especially maybe in states that aren't by oceans or that are kind of getting missed, that, with, seminars and stuff, it's like much easier nowadays that we could be pulling in lots of other students. Like, I'm from Ohio, like I didn't really even know you could study marine chemistry until I became a grad student.
That's a great point, Katelyn. And we're losing them to other industries. Like I have 2 students who are working in wine and vit right now because they can do analytical chemistry in the wine industry and be paid. But I think a little bit part of the problem, sorry, how do I explain this? Undergraduates want to know what job they can get in the future, right? And it's hard to explain to them what job they can possibly get in marine science in the future as an analytical chemist, even one with an advanced degree, if they don't want to be a professor. And I think a little bit this problem might be solving itself with the emergence of MCDR, and that feels to me like that's going to be a huge industry which needs to employ a lot of chemists. And so if we can sell it, kind of like, Erica said, maybe webinars or some sort of way to excite students from Ohio about this stuff. Something different from when I was an undergrad, also a chemist, was that students now get environmental science training in high school, right? Like I didn't take environmental science really until I got to graduate school or undergraduate. And so they kind of do care. Like I find broadly, they actually would love to fix the world. They just don't know how. And so if we can sell them that by studying the nitty gritty of physical chemistry to help contribute to this, which will help understand this model, I think there's a possibility there. But yeah, so maybe communication is one of our, I guess that was number 2 of that mechanism, but. I kind of agree. Yeah.
Heather, are you seeing any questions?
Here we go. So we have a question in the Q&A. I have a 40-year career in applied marine science, mostly in fisheries, but also water quality issues and blue carbon issues for the UK seafood industry. And I have cause to be grateful for the marine chemistry I learned as an undergraduate. Not that I use it every day, but I feel comfortable with the concepts and their interpretation for the seafood industry. So communication and the idea of recruitment, but also communicating why these fundamentals are critical in those applied science fields, I think, and helping people make that connection back to these fundamental, bedrock that we rely on to be able to do things like acidification or studying, do MCDR field trials. You need to have that fundamental understanding of basic chemistry to do those things. So we need to build the awareness at the undergrad level about career paths and also help them understand the importance of specializing in a field, being able to understand that you have to have that fundamental chemistry background in order to use the sensors, interpret the data, and make decisions.
Okay.
Bill, are you able to unmute? I'm not sure if, Katerina, can you unmute Bill, or are we unable to unmute our?
Bill, you should be able to talk now.
Hello, can everybody hear me?
Yes, you're good.
Right, okay, yeah. So my training was mostly marine biology and oceanography, mostly chemical oceanography, and it was very broad. But we did some very in-depth stuff on the physical chemistry, which has actually set me in very good stead. Not that I've done a little tiny bit of analytical chemistry, but just the confidence that you know what an oxygen meter is doing has been useful to me, basically, and I hope others pick up this sort of knowledge and use it. So that's really my message is that that training 40 years ago has not been wasted, and that more undergraduates should do it. Is that helpful?
Oh, it's helpful. Thank you.
Yeah.
Absolutely.
And I think, Bill, that highlights a whole other industry we didn't even say, right? Like anything around sustainable aquaculture, fisheries, food security. Like we haven't even gone that direction yet, but that is a huge industry and obviously one that is in need of water quality monitoring related to all of these things.
Yeah, basically, it is the scope for people in marine science to go into looking at sustainable fisheries, or, as you say, sustainable aquaculture has just mushroomed since I started, and it's helpful if they have some background in this marine chemistry field. You don't have to be too advanced, but you do need to know fundamentals. That's the message I have for the kind of work I do anyway.
Yeah.
Okay.
Thanks. So, Katharina, quick question for you. When are we, going to be cut off? How much time do we have?
I can give you another 20 minutes, but we have another session scheduled after this. So that's the absolute ultimate
Okay.
cutoff point, I'm afraid.
Okay. So perhaps what we should do then for the remainder of the time, which we'd intended to we have questions to focus more upon the workshop itself and how we should be aiming to construct it and the participants and so on. Perhaps Heather, we should sort of conflate those different elements rather than divide them up into 5 minutes each, because that doesn't seem that doesn't seem quite long enough. So I'll move on from I'll go through these slides, hopefully slowly enough so that people can retain them. And the first thing we were going to bring up are to ask explicitly what should be the workshop goals. And we thought the obvious things would be identify the key areas and specific skills that are lacking and the impacts that's having. And then, well, the content of the workshop is to figure out how to address these in research and teaching. And the question following on from that would be, who do we want at the workshop to do this? And our thoughts were that we need to be diverse in terms of fields and applications, range of career stages, and globally distributed representation as far as we can. And we thought that, of course, there should be chemical oceanographers, but there should be representatives also of the other science disciplines who bring the chemistry, metrology, expertise, and skills that we're seeking. So, for example, in my specialism, speciation modeling, in geochemistry more widely, and in chemical engineering, there are still the people who know, the experts who still know about that, and it would be great to get them interested in chemical oceanography. Other people we would like to draw in would be employers outside of academia, funding agencies, chemistry organizations, and capacity building organizations. So those were our ideas for the participants. Moving on to the format and organization, we thought to form a small international leadership team to organize this rather than it just be us. I think we can do better by broadening out and have a 2, possibly 3-day hybrid workshop, but we'd strongly prefer people to be there in person, simply because conversations are needed. There would be an advanced preparation and homework for participants. So this would not be a trivial thing to take part in, and also it would avoid something that I particularly dislike, which is to turn up somewhere with a blank sheet of paper, a blank mind, and then be told form a breakout group. I think that rarely leads to success. And finally, moving on from format and organization to what we thought of the workshop outputs. Well, clearly a report or a white paper summarizing the problem and what we think can be done to address it. And it should be something sufficiently broad to be worth sharing with Earth and Ocean Sciences, ocean science teaching programs, funding agencies, and with industry. And those were our ideas. I'll just move back to the first one of those and remind you. So it was the outputs, the format and organization, the participants, and the goals are what we'd like to focus on for the remainder of our time. So focusing on the workshop, what do the panel think and others are essential aspects of this that we really must have, and that perhaps we haven't put on our slide. Oh, there must be something.
There's a lot coming in on the Google Doc. Jeff, go ahead.
Yeah, so I would say that one of the things that I think I heard here that I liked the most was meet people where they're at. Like if there's a group that really is the experts around speciation generally, whether that's the inorganic carbon system or whether it's trace metals, the working group did this fantastic job of making marine chem spec and using the Pitzer approach to do that. I would say one goal of the workshop would be to create a paper, a document, something that I don't even know that has to go through a review process. That is like, here are the basics. Like when you write out a chemical equation and you define an equilibrium constant, and then you decide that you want to have activity coefficients, what goes into those activity coefficients? Why we break this out as having a sort of universal reference point for folks to go to. I think we would capture those chemists that are inquisitive about how they could do something in the oceans or something more applied, or use their physical chemistry. And we would make a thing that is quite useful. And I think other fields have done this. I know where to point students when they are trying to get the basics of physical oceanography and how it might interact with the biogeochemistry. I think that Williams and Follow's book is really good. They're equivalent things in meteorology. Why not make something like that from a physical chemistry point of view? Like instead of being sort of bummed about what people don't know, let's show them what we think we know and how they can easily ingest it.
Okay, so some of the things that are now mainly conceived and thought of as research tools should also have a strong teaching element to them, so that people who don't come with the expertise, which will be most people, can in fact learn the basics and therefore not misuse these things and get something positive from them. Right.
Go ahead, Cliff.
Yeah, I was just going to follow on with that. I mean, I think there's a lot of value in providing a centralized resource. Two observations from my career is that I had always thought faculty or professors thrived on creating brand new content, but then I suddenly learned through experience that most of the time they're cannibalizing other resources to make their own courses, or copying concepts that work. And so kind of centralizing those resources would be a real service, I think. I mean, I know in my own experience, I've borrowed Andrew Dixon's PowerPoint that you can find on Google on ocean acidification and DIC chemistry, because it's a really digestible way to share with students, and not have to kind of reinvent the wheel. But so I think I would just add, in terms of workshop goals, or really on the kind of the preparation side, as Simon said, it's nothing worse than showing up and there's no plan of action, nobody's prepared. But on the preparation side would be to kind of think holistically about specifically what are the important aspects. I mean, just saying kind of, marine physical chemistry, I mean, that's huge. There's lots of concepts there, but maybe we could kind of triage and figure out which are the ones that are truly, the fundamental basics that could be included in a centralized way.
Yeah. Okay. Thanks, Clifton. You seeing anything in the chat, Heather? Oop, you're muted.
Not at the moment, but the Google Doc is very active. Keep it going, everybody. This is really, really helpful for us.
Okay. Well, I'll throw something to the panel and to others. I thought, what if we, the field, someone wanted to do things very, very quickly? What are things that might make quick gains? And so I thought, on the teaching side, and I guess this would be aimed at graduate and or PhD students and early career postdocs, would be summer school in these fields. I mean, there are successful examples in plenty of fields. And then I thought, well, research opportunities. And when I raised the idea of a sort of focused funding program with NSF in the context of this whole skills gap question, I was given the kind of obvious response, or obvious in retrospect, was that, well, if there are too few people with these skills, then what's the point of having a solicitation when there are unlikely to be enough or perhaps sufficiently informed proposals put in. But I mean, I thought if one did want to create such a program, then one way of doing it would be to make a condition or a strong preference for bringing in some of those experts from other fields who can still do the things, who have the expertise that we're missing, and so bring them back into the field, not just through teaching or teaching materials, but also through research opportunities. And I guess if you have the right funding mechanism, PhD opportunities attached to such projects. So those were just a couple of sort of very general thoughts of mine.
Simon, just to follow on that, I couldn't agree more. I think that the summer schools that are offered in our community are really formative experiences. I also want to make a plug, because I had a very formative research experience as an undergraduate that really set me up well, and it gave me that appreciation of that drilling down and really understanding a fundamental discipline as it's applied more broadly to interdisciplinary science or problem solving in whatever sector that you would build a career path in. But in thinking along the pipeline, I will forever stand on the soapbox that research experiences at the undergraduate level are absolutely just game changing for a lot of students. And I think it's a great way to learn the material in a way that you can't do so in a classroom. And I think it's a great recruitment tool and helping students really understand the applications of these fundamental disciplines like math and chemistry and biology. And so I love that we have people like Emily, you know, in the field teaching at that undergraduate level and building those skills and building that excitement about this career, a research career or a research pathway. And it doesn't have to be confined to academia now. There are a lot of big problems that we need to solve that some of our participants today have brought up. So that's my plug. Go ahead, Emily.
Yeah, this actually wasn't even what I was going to say, but I'll second that. I mean, I'm accidentally creating like a team of carbonate chemists, right? That like want, because it's what I study, right? But I keep trying to convince them, like, no, there's so much other cool chemistry in the ocean. Like, you don't have to be a carbonate chemist. Like, you can study trace metals. Like, there's so many other things. But I think what that does is just speaks to, they do get really excited to what they get exposed to. So that makes me think, to answer Simon's question about what are quick things we could do, what about some sort of like chemistry, marine chemistry based RU program? I don't know. I mean, I know RU, maybe it has a different word because we would have to bring experts to the same place to advise those students or something. But instead of necessarily just at the graduate level, like we could do a summer research experience that brings undergraduate chemists specifically, right, from different institutions to one place to get these sort of experiences early in their career. That could be a way to like really excitement and create future graduate students. So that's kind of one idea. The other thing that I was going to mention, which is sort of what Simon said, but an adjustment to it, is maybe summer schools for graduate students are great. You know, I got to participate in one at Friday Harbor. That was great. But we also do now live in this post-COVID era of Zoom and Zoom education, and no one loves taking a course on Zoom. But I wonder if we could solve graduate level advanced chemistry enrollment problems by pairing institutions, right? Someone at one institution teaches a course that pulls advanced grad marine chem students from 5 different institutions. So there are 10 students excited in taking the same course, and that professor now gets to teach actually in their expertise what they're excited about and dig into some of these harder concepts because they do have the grad level chemists in the room, and we can build education that way. And so I wonder it's just hard. I mean, you know, I was so lucky to work with Andrew and to get exposure to some of this physical chemistry, but like there were only 3 chemists in my cohort at Scripps, right? The beauty of ocean science is its interdisciplinary nature, but this is also causing a lot of our problems, right? Like we are spread out. And so I wonder if, even though I hate teaching on Zoom, if we could teach on Zoom to bring chemists together.
And maybe to like make it more exciting, you add on to that Zoom course like an in-person like one thing. I don't know, or maybe you meet up at an AGU or you meet up at an Ocean Sciences. And I don't know. I'm just, it would be great to also add an in-person component to make it a little bit more attractive.
Okay. Somebody else. Okay, so I'd like to put a question to Erica. You may, well, I've been focusing on the the mechanics of this afternoon, so I may not have heard everything given everything you said the attention I should have. But what, from your perspective, or from the funding agency perspective, are obvious? Are there obvious skills gaps? How do they manifest themselves? And I threw out a few ideas for quick actions, such as targeted funding programs with certain conditions or preferences attached. How does that sound to you?
I mean, I do
sensible?
that all the time.
Pardon me?
I do that all the time with my funding program, is have like, if I'm missing social scientists, I make it a requirement that like the physical and natural sciences work with the social science. So I think that's something that I do in my program all the time. I don't know if that will work in all agencies, but it's definitely a recommendation. And if it comes bottom up from the community, that may be something that other agencies are more willing to accept if it's coming to them in that way. But from NOAA's perspective, hearing these challenges of the community, it's definitely something I'm going to go and bring back to the other programs who work in this space, the Global Ocean Observing and Monitoring Program, but also the labs, the NOAA labs that also house some of the leaders in the field, right, where Katelyn is now working and doing her postdoc, and figuring out, are there other opportunities? I think NOAA does a great job of offering paid undergraduate fellowships, the Halling Scholarship, and there's graduate scholarships that NOAA offers as well, either in conjunction with sanctuaries or with other programs. So figuring out how, or if we could utilize those opportunities that exist and are paid for already to maybe get some additional carbonate chemistry focused capacity as well. So these are things I'll be talking about and thinking with my colleagues, but do want to say that there is some flexibility in how we do things, and every program and every agency is a little bit different.
Okay, thank you very much.
I really hate to do this because this conversation is going so well, and I think the discussion is absolutely, it's so valuable to the whole community. However, we are absolutely running out of time, and we have another session lined up. So I would like to just encourage everybody to use the Google Docs, jot your ideas down there. The whole session has been recorded, and we will upload it to YouTube. We will share the link widely, so you can look over this again and maybe keep contributing to the Google Doc, and definitely reach out to all of our panelists with your thoughts and ideas. So with that, thank you all so very much, both to our audience members who were numerous, and to all of our excellent panelists, to the organizers, and we hope to see you again very soon. Thank you so much. Goodbye.
Thank you, everyone, so much.
Bye-bye.
Thanks.